So today we are going to see the operation of single phase fully controlled rectifier with RL load and freewheeling diode. So this is the freewheeling diode which is connected in parallel to the load. So this is called freewheeling diode since it is used for the dissipating the energy stored in the inductance during the positive half cycle and also in the negative half cycle. So the freewheeling diode performs the freewheeling action, that is to dissipate the energy stored in the inductance. So it provides alternate path for the dissipation of that energy. So it will conduct during that period alone. For the dissipation of energy stored in the inductance, the freewheeling diode will conduct. And during remaining time periods, the freewheeling diode will be in reverse bias condition. Only during the dissipation of energy, the freewheeling diode will come into action and it will conduct. So first we can see the normal operation of this single phase fully controlled converter. That is, for positive half cycle, the thyristors 1 and 4 are forward biased. So the current will flow through this from positive to, that is, SCR1 and R and L, and then to SCR4 to the minus terminal, that is neutral terminal. So here during this time the inductance will store energy with the polarity with upper end as positive and lower end as negative. So from the period of alpha to pi, the thyristors 2 thyristors 1 and 4 are forward biased from 0 to pi, but it will start the conduction after the triggering angle or after giving the firing pulses. So the firing pulses is given at an angle of alpha, so it will conduct from alpha to pi. So the CRs responsible for this time period is 1 and 4, that is oppositely paired thyristors, that is 1 and 4 will conduct from alpha to pi. During that time the inductance will store the energy with the polarity like this, and at the end of this positive half cycle, that is pi, the voltage input voltage polarity reverses, that is the negative cycle will comes. So during this condition, suddenly it will the inductance will suddenly opposes the change in direction of current, so that the inductance polarity gets reversed. So here it will be negative and it will be positive. So this polarity of the inductance, now the two SCRs will be in turn off condition and the SCR 2 and 3 are in forward bias but still not triggered. So 4 SCRs will be in off condition, and this negative voltage is applied to the cathode of the freewheeling diode and the positive is applied to the anode of the freewheeling diode. So due to this freewheeling action, the due to this polarity of the inductance, the freewheeling diode will comes into forward bias. So due to that, it will act as short circuit and it will provide the path for the dissipation of the energy. So here the energy will flow, or the current from this inductance will flow in this upward direction in freewheeling diode and it will comes the downward direction in the load. So this will provide an alternating circulating current path for the dissipation of energy. So this is the circulating path, that is R, L and freewheeling diode. So the current flows in upward direction in freewheeling diode and it comes downwards in the direction of in this load, and it will dissipates fully the energy only in this path. There will not be any energy or conduction of this SCRs, already conducting SCRs. In previous cases, already conducting SCRs will conduct to dissipate the energy stored in the inductance and the energy will be fed back to the source. But here, if the freewheeling diode is connected across the load, means the inductance stored energy will dissipated through this freewheeling diode. So the remaining SCRs will be in off condition during that freewheeling action, that is the dissipation of energy. So here we can see from pi to pi plus alpha, the freewheeling diode will conduct and the inductance stored energy will gets dissipated during this period. So pi to pi plus alpha. So in previous case, in the RL load, we will get we got some negative spikes. So this negative spikes is gets eliminated in the case of freewheeling diode. So if the freewheeling diode is connected during this period pi to pi plus alpha, if the freewheeling diode is connected means, so that will provide short circuit path across the R and L, so that there not be any negative spikes during that period. So it is short circuited by the freewheeling diode, so the negative spikes are avoided. So the advantage of the freewheeling diode is it provides alternate path for the freewheeling action of the energy stored in the inductance, and also it eliminates the negative spikes from the output voltage. So during this period there will not be any negative spikes, we will get only the positive output. And the next half cycle, for the negative half cycle, the conducting thyristors are 2 and 3. So the current flow will be, the positive is in this lower terminal and negative will be in upper terminal. So from the positive, the current will flow through SCR2 R L, and then it will return through this third thyristor SCR3, and it will return to this negative terminal. So during this kind of time also, the inductance will store the energy with upper end as positive and lower end as negative. And after the time period, that is after the end of the negative half cycle, and that is after 2 pi, the polarity will get reversed, that is minus and plus. Again the energy stored in the inductance will get dissipated in this path, that is RL and freewheeling diode. So the from the period of 2 pi to 2 pi plus alpha, again the freewheeling diode will be conducting. So here we can see from alpha to pi, positive half cycle, the conducting thyristors are 1 and 4, and pi to pi plus alpha, the energy will get dissipated, and it is dissipated in freewheeling diode, and only the device which is conducting is freewheeling diode. And pi plus alpha to 2 pi, the conducting thyristors are 2 and 3, and the energy dissipation of the after the negative half cycle is due to the freewheeling diode, and here the conducting device only is freewheeling diode. Again the positive half cycle, the 1 and 4. So this will repeatedly continues, and here we are not getting any negative spikes, but we can see the difference. So there is no negative voltage, means we are getting somewhat pure DC than the previous case, and the current is flowing. So here we are having zero voltage, but still current is flowing due to the dissipation of this inductance stored energy. So we are having the current over the full time period. So here from pi to pi plus alpha, the voltage is zero since it is short circuited by this freewheeling diode, but the current will flows through this, or due to this energy stored in the inductance, the current will continuously flowing from pi to pi plus alpha. The energy due to the energy stored in the inductance, the current will flow, and pi to pi plus alpha to 2 pi, from the supply source we are getting the current. So alternately, for the conduction period or for the charging period of the inductance, it will draw the current from the source, and for the discharging period of the inductance, the inductance will discharge, and the current will flows from the inductance to the load. Anyway, we are getting the continuous current for this freewheeling diode. So the only difference is we are not getting any negative spikes, so that somewhat pure DC than the previous case we are obtaining, and the I naught, that is the output current, will be continuous. So this is the ID, that is the diode current. So what are all the periods the diode will be conducting is first 0 to alpha. It is the previous period. Here we can see 2 pi plus alpha to 2 pi. So this is the previous period of this. So before the conduction of 1 and 4, obviously the freewheeling diode will be conducting. So here the diode current will flows, and this condition alpha to pi, the diode current is 0. Pi to pi plus alpha, again the diode conducts, and 2 pi to 2 pi plus alpha, again the diode conducts. So this is the diode current, and the diode current's magnitude is shown over here. So this can be realized using the PSIM. So yesterday we have drawn this circuit. So in that we can connect some freewheeling diode in parallel to the load. So we can have the some diode across the load. For connecting the load, we are making some arrangements. So we have to connect a diode in parallel to the load. So this is called the freewheeling diode. So the cathode will be in a upper end and the anode will be in lower end. So in this way we have to connect the freewheeling diode. So Now we have connected, and we have to name it as freewheeling diode FWD. And we can see the current of this freewheeling diode by making the current flag of the freewheeling diode. If you double click this freewheeling diode, means its box will this dialog box will open. So here we can alter the parameters. We have renamed it as freewheeling diode FWD, and we can make it as 1, so that we can also obtain the current through this freewheeling diode whenever the freewheeling diode conducts. So that can be obtained from the diode. Okay, so now we can run. So first one, we can see the input voltage. So that is the sinusoidal waveform. Already we have seen with the maximum magnitude of 325. And the second one is V naught. V naught here we can see, although we are connecting the inductive load with an inductance of 10 Henry and the resistance of 10 ohms. If we connect the inductance, means we will get definitely a negative spikes. And now due to the connection of this freewheeling diode, the negative spikes gets eliminated, and only we are getting the positive output. And then we can see the current. So this is the type of current. So here we are having some zero voltage. So in that zero voltage period, though there will not be any current, that is current is 0. And we can see the freewheeling diode current. So we can obtain, you can see during this period, during this zero voltage period, we are getting the zero current, the diode current, that is freewheeling diode current, will be flowing during this period. That is, so this is the alpha to pi normal conduction, pi to pi plus alpha, the freewheeling diode conduction. During this condition, the current will through this freewheeling diode will gets flow through that diode. So it is here we are getting the zero current, means the energy or the inductance energy is suddenly gets dissipated in this period. So it is drastically reduced to 0, and we are getting the zero current. So it regards the time constant, so that we can increase the resistance, and again we can run. So it is the ideal case, so that the current is drastically reduced to 0. So here we can reduce 0.01. Okay, so here it is near relevant, it is the same as that of the resistive load. So it is very low value, so it is the same as that of the resistive load. So we can increase 0.1. So here we can see, so the inductance energy is suddenly dissipated due to this diode. The freewheeling diode is conducting for this region. So during this region, the inductance energy suddenly gets dissipated. So, but in practical cases, it will take some time to dissipate. But in this simulation, it is an ideal case, so that it is suddenly gets dissipated. So here we are having the diode resistance as 0. So if the diode resistance is 0, means, so it provides an accurate short circuit. So due to that, the current will suddenly short circuit, the energy stored in the inductance is suddenly short circuited, and it suddenly gets 0. If we are increasing this diode resistance, so randomly we can have diode resistance as 1 ohms. So that will take some time to dissipate that energy. So here also, if you are going on increasing, means, so then we will get some extra time for the dissipation. So here we are having some what distorted. So depending upon this resistance, diode threshold voltage and diode resistance, we will have the, so it will not be 100 ohms, it will be nearly 10 ohms. So that for the practical cases, we will have the, for example, we can alter but in practical cases it will not be this much high, the diode resistance, right? So it will take some time to reach the zero, and here we can eliminate this zero period by means of increasing that diode resistance. So this is the freewheeling diode action. And the next case we can connect, so in this circuit we can connect some that is a DC battery, there is a RLE load. For RLE load, we have to connect some battery across this load. So simply we can have this battery source, and we can connect this, and we can give some 100 volt as amplitude of this battery. So due to this inclusion of the battery, so let us see what will be the difference in the output. So first thing, we can see the input voltage, it is sinusoidal waveform. Then next one, we can see the output voltage, and the third one we can see the output current. So here we are seeing that from alpha, this is the alpha, that is we have taken the alpha as 30 degrees. So from 30 degrees to, that is 30 degrees, for 30 degrees what will be the time in time magnitude means it will be 1.63 milliseconds. From 1.63 milliseconds to nearly 10 milliseconds, the SCRs 1 and 4 will be conducting, and pi to pi plus alpha, the inductance will be dissipated, and after that, so we have to obtain zero voltage period, but instead of that we are getting the definite magnitude, that is 100 volts, since the voltmeter, that is the voltage probe, is connected across the load. Here we are having the load as R, L and E, and during the non-conduction period, if all the thyristors are not conducting means, so at that condition the voltage measured across this probe will be the 100 volts. So at this condition, instead of 0 volt we are getting the 100 volts. So in the same time, and after this 100 volts only, the device will starts the conduction. So if we are having the if we observe this T4 thyristor means, so it is connected 100 volt to the anode, and this 100 volt is connected to the anode of the T3. So whenever the supply voltage exceeds the 100 volt, these two devices will get forward bias. Suppose for the positive half cycle, the T4 will be forward biased from 0 to pi, that is from the for the positive half cycle. So from 0 to pi, T1 and T4 will be forward biased, but it is fired at an angle of 30 degree. In 30 degree also we are having two voltages in this circuit, that is 100 is connected to the anode, and the voltage, that is sinusoidal input voltage, is connected to the cathode of T4. So when the T4 starts the conduction means, so here 100 volt is applied, so here sinusoidal voltage, varying voltage is applied. So whenever the voltage whichever is positive at this anode will be the forward bias of this T4. So when here, when this 100 volt and this is sinusoidal volt, so whenever the input voltage exceeds this 100 volts, the the CR will start the conduction. So here we are having the, instead of 0 voltage we are having the 100 volts at the after the dissipation period. Instead of here, if you disconnect this, so if you are disconnecting this means simply the RL load. So in this RL load we can run this means, so we are having the 0 volts. So alpha to pi, normal conduction 1 and 4, and this small spikes will be the dissipation of the inductance energy, and there will be some definite zero period, that is discontinuous conduction. So up to this also we are having the 0 voltage period. So here we are having the if we connect the battery source of 100 volts means, so instead of that zero period, the voltage is shifted to 100 volts. So here we can see the zero voltage level is shifted to 100 volts. So the RLE load, for the RLE load, they are having the practical example as the motors. So for the motors will have these three parameters: resistance, inductance, and the battery. The battery is nothing but the back EMF of the motor. So for the drive applications, we will go for this RLE type of loads. So in RLE type of loads also, we will have two types of conduction modes, that is in discontinuous conduction and the continuous conduction modes. So this will be useful in deriving, or it will be analyzing the RLE type of load, that is motor loads. We can analyze by using this RLE parameters. Simply we can measure the resistance of the motor, inductance of the motor, and the back EMF of the motor. So by accordingly we can design the motor equivalent circuit. So and we can apply for this, and we can study the output parameters from this circuit. Thank you.